Maybe a little bit less silly than the last example, but still in the same spirit here. Maybe you think it's more silly. Suppose S is the light bulb shaped region here, with base x squared plus y squared is equal to 1 in the xy plane. Normal oriented outwards here. Evaluate the double integral of the curl of f dot n d sigma for this vector field here. So what's going on? This is exactly set up for Stokes' theorem. So this is asking us for the right side of Stokes' theorem. We don't have to compute the curl here. That's meaningless. We don't have to do anything without how the heck are we going to parameterize this. I can make this as silly as I want to. It doesn't matter. This particular surface doesn't matter. The only thing that matters is how it's oriented outwards, and the boundary here is x squared plus y squared is equal to 1 in the xy plane. So all we have to do is compute this. How do we do that? Well, we need to parameterize the circle in the xy plane. We can do that. R of t is cosine t, sine t, and 0. This is z is equal to 0 here. T is running between 0 and 2 pi. We know we'll need r prime of t, negative sine t, cosine t, and 0. And we need to substitute in r of t in up here to f. So f of r of t is going to be, now let's see here, e to the z squared minus 2z. That looks messy, but we're replacing z with 0. E to the 0 is just 1. X becomes cosine t. Sine of xyz, sine of cosine t times sine t times 0. Sine of 0 is 0. Plus y is sine t plus 1. And then e to the z squared plus, e to the 0 squared plus 2 sine t plus cosine t times sine of z squared, but again, z is 0. So there we go. Look at how nicely this is simplifying here. This feels like it would be a mess, even I gave you some hope of parameterizing the surface here. You'd have to do the curl, and you have to do a very, very, very difficult double integral here. This is shaping up to be a breeze here, thanks to Stokes' theorem. Okay, so we've got f of r of t here. We need f dot r prime of t. And this will be, so this dot this will give us negative sine t cosine t plus sine t times cosine t plus 1 times cosine t. And those cancel. And if I haven't botched up anything here, this just ends up as cosine t. So our integral is the integral from 0 to pi of cosine t dt, and we get 0. So look at that. Looks really messy here. Now I should say this was more of an accident that this ended up as 0. You shouldn't think that this is the same thing as the previous problem where just because where it was like the closed surface here that we got 0. This is not a closed surface. We do have to do that integral. It just so happens that that integral ends up giving us 0 here.